The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So today we're going to continue our course on graph theory. It's going to be a mixture of all kinds of topics. We first start off with Euler Tours, and then we get into directed graphs and cover the definitions. And we'll talk about a special type, which are called tournament graphs. And we will do a whole bunch of proofs, and hopefully you will all contribute to make this work and think about how to do this. So next week we will continue with graph theory, and we will discuss a very special type. We will use directed graphs in communication networks, and then on Thursday we will actually use these special types of graphs that I will talk about in a moment, Dijks. Okay, so let's talk about Euler Tours. And well, Euler, a famous mathematician, he asked a question like, he lived in Königsberg, and there were 7 bridges, and he was wondering, can you traverse all the bridges exactly once? So he would start walking and try to cross all those bridges, and apparently there's a little island in sort of the river as well, and so on. So how can you do that? And this was actually the birth of graph theory, and this particular problem is named after him. So what is an Euler Tour? It's actually defined as a special walk It's a walk that traverses every edge exactly once. So it turns out that we can actually characterize these types of graphs. So we're talking here about undirected graphs, so continuation of last time. So the edges that we consider have no direction. We will come back to that in a moment. We will start defining those later. So an Euler Tour is a walk that traverses every edge exactly once. And at the same time, it's also a tour. So that means that it actually starts and finishes at the same vertex. Now, it turns out that undirected graphs, the graphs that we've been talking about, they can be, those that have Euler Tours can be easily characterized. And that's the theorem that we're going to prove next. The theorem states that actually, if a connected graph has an Euler Tour, if and only if every vertex of the graph has even degree. So that's a very nice and simple and straightforward characterization. So how can we prove this? So let's have a look. So first of all, we have an if and only if statement. So we need to prove 2 directions. We need to prove that if I have a connected graph that has an Euler Tour, I need to show that every vertex has even degree. And also the reverse. If I have a graph for which every vertex has even degree, I need to show that it has an Euler Tour. So the proof consists of 2 parts. So let's first do this implication, where we assume that we have a connected graph that has an Euler Tour. So assume we have a graph. So we have G with a vertex set V, edge set E, and it has an Euler Tour. So what does it mean? Well, It really means that we can walk from some start vertex, V0. We can go all the way around to V1 and some more, and so on, to V, say, k minus 1. And then the end vertex is the same as the start vertex. So we have a walk that goes all around the whole graph. So every edge in this walk are exactly the edges that are in the graph. And each edge in the graph is covered exactly once. So what does it mean? So let's write this down, actually. So since every edge is traversed once, every edge in E is traversed once, what can we conclude from that? Can we say something about, given such a cycle, such a cycle of length or walk of length k, what can we say about the number of edges, for example? What can we say about the degree of the vertices? Because that's what we want to show, right? We want to show that every vertex has even degree. Does anyone know how to go ahead here? So we know that every single edge in E is traversed once within this whole walk. So what kind of properties can we derive?
If you enter a vertex, you have to leave it.
That's true.
So this means that.
So maybe someone else can pick up here. So every vertex that I have here, I will enter it, but I also leave it. So if I see a vertex in here, I can see at least two contributing edges that are coming from this. Okay?
Then you know that that node has at least degree 2, but it can't be more than 2 because otherwise that would be the endpoint.
But is it true though that, so for example, this particular node here may repeat itself somewhere else. I only have a condition on the Euler Tour that every edge occurs exactly once. So how could I formally sort of continue the proof?
Then it'll intersect itself again, and then it'll leave again, and it'll still have even degree.
Yeah, that's true. That's right. And any other additions?
You can define the number of edges that a node has by how many times you enter it.
Mm-hmm.
So the number of edges that a node has is twice the number of times it's entered.
Mm-hmm. Yeah, that's correct. So that's sort of how it goes.
Well, since you know every edge is only traversed once, then and every time you enter a node, you have to leave it.
Yeah.
So you can say that you're never going to leave a node for a node that it already left from there, and you're never going to enter from a node you already entered from or left to from there. So that's how you can say that you're only going to increment your your instances by 2, or your degree by 2.
Yeah, that's true. So what you're essentially saying is that every edge that I start to count here in this particular tour, well, they're all different, so they all count towards the degree of a node. So, yeah, so everything that you have been saying is right on. So what we can conclude here is that if we look at a vertex, say a vertex U, for example, somewhere over here, well, it may repeat itself over here, and it has an incoming and an outgoing edge, incoming and an outgoing edge, and I may have it somewhere else, but say I just have those two. Well, I know that all the edges are different, so I can clearly count this now. I can say that the degree of U must be equal to the number of times that U actually appears in this tour. And so in the tour from V0 all the way to Vk minus 1. And then I have to multiply times 2. And why is that? It's exactly what you have been saying. All the edges occur exactly once of the whole graph. So I just count the number of times I see U in here. I count the number of edges that go into it and leave from it, well, it's twice times the number of times that U actually appears in this tour. So this implication is pretty straightforward, because now we actually know that the degree of U is even. So that's great. So let's talk about the other implication and see whether we can find a trick to make that happen. So what do we need to start off with? Now we have to assume that every vertex has even degree. So let's write this down. So say we have a graph. And for this graph, we actually assume that the degree of every vertex V is even. Well, what can we do? So, well, this is sort of a creative trick, so let me just continue here. So what we have is, if you start to consider a walk, W, that touches, say, a lot of vertices, in such a way that W is actually the longest walk. So that's often what you do in graph theory. You think about, say, the shortest path or whatever with a certain property, or the longest walk or whatever with a certain property. So that's what we're doing here. So let W be the longest walk. And, well, we want to prove something about an Euler Tour. An Euler Tour has a very specific property that all the edges occur only once. So it makes sense to look at walks that have, in which all the edges over which it walks are unique, are occurring only once. So we are interested in the longest walk that traverses no edge more than once. So that's important. Now let's think about this a little bit. So the first property that we may want to consider is, well, we really want to show that W is going to be an Euler Tour. That's what we're going to try to prove here. So the first thing we may want to show is that actually it goes all around. So V0 is equal to Vk. That would be great if we can do this. So we want to show that this is true. So what would happen if this would not be the case? So, so suppose these two would not be equal to one another. Well, oh, actually, I'm skipping a little bit ahead here in the proof, I notice. So this will be the conclusion of another observation. So let me start with the first observation. So first of all, let us consider this end node over here, this end vertex, Vk. Now, if there is an edge that is not covered in this walk, then I can lengthen the walk, right? So if I have, say, another edge, which looks like Vk, an edge from Vk to some U, where this edge is not in the walk, or the other one is not in the walk. Well, it doesn't matter in an undirected graph, of course. Okay, so if this is not in the walk, then what can I do? I can just lengthen it, right? I can just say V0 goes to V1, goes to Vk, goes to U. Now I have a longer walk, and that's a contradiction. So I know that all the edges that in which Vk is participating are actually covered by the walk. So that's a great property. So let's write this down. So all edges that are incident to Vk are actually used traversed in the walk W. So now let's have a look whether we can show that it's actually a walk that goes all the way around. So let's try to prove this statement. So let me repeat this over here. So what we want to show is that Vk equals V0. So given this statement, do you have any idea how we could possibly prove this? Also given what we have been doing over here. Like, suppose this would not be the case, right? So suppose the start and the end node in this walk are not equal to one another. So what can we do here? So maybe there's some suggestions. I already had you once. Maybe someone else? Oh, why don't you...
It has to attach to another vertex, and you know that all the degrees are even, so it means that Vk must attach to V0.
So what you're saying, first of all, is that if this would not be the case, right, then you know that well, you say you know that the degrees must be even, but suppose this would not be the case, that would mean actually that the degree would be odd, right? Okay, so let's think about that a little bit. So let's write this down. So otherwise, Vk has odd degree, but we only know it has odd degree in this particular walk W. So that's what we do now, because we really consider this walk. It's just this. Where did I put it? It's right here. So we see that if I have V0 unequal to Vk, then Vk may be repeated in this walk a number of times. Each time it is repeated, there's an incoming and an outgoing edge. And all these edges are different because they do not occur more than once. So whenever Vk enters in this middle part over here, is partaking over here, it gives an even contribution to the number of edges in this walk. And it has one extra incoming edge over here. So if V0 is not equal to Vk, we will have an odd degree of edges in W, in which Vk is participating. So now we can go ahead and we can have a look over here, because we just showed here that all the edges incident to Vk are actually used in W. So we can now conclude that this means that Vk also has odd degree in G, because all the edges in G, in which Vk is participating, are actually used in the walk. So I hope that is clear. Okay, so let's write this down. So we will use the first statement over here. So by 1, we have that Vk has odd degree in G. And now we come to what you were saying. We have assumed over here that the degree is even. So this cannot be the case. So that's a contradiction. So we know that the otherwise situation cannot occur. So we know that Vk must be equal to V0. So that's proving that we actually have a walk that goes all around. Now we are not yet done, because why would this be an Euler Tour? For an Euler Tour, we really want that every single edge that G has is actually used in the tour. So we need much more. Okay, so let's use this word. Okay. So suppose that W is not an Euler Tour. We're going to use contradiction. But we already have shown this particular property, so we can use this. So suppose W is not an Euler Tour. Well, we know that G is connected. So that's a good thing, because that means that if it is not an Euler Tour, there is an edge that is not used in W, in the walk, but it is incident to some vertex. To some vertex that is used in W. So this is where the connectivity comes in play. Now let us call this edge. So let U VI be this particular edge. So U is not used in the walk. Well, it may be used in the walk, but the edge is not used in the walk, and VI is part of the walk. So what can we do here? So does anybody see what we could do here? Can we somehow get a contradiction? So when we started out here, we actually assumed that W is the longest walk that in which the edges do not occur more than once. Can we create a longer walk by simply using this? Now notice that we did prove that V0 goes all around to Vk and so on. So can we find a longer walk that uses this extra edge? Any ideas? What would happen if we, for example, would start a walk with U? Let's see how that would work out. We can have U, we walk to Vi. Well, let's then just simply start walking all around. So essentially we have Vi over here and U over here. So what we could do is we can start walking like this and then end over here. And notice we have used one extra edge. So we get a longer walk. So we go to Vi plus 1 and we go all the way up to Vk, which is equal to V0, and then we go up to V1 all the way up to Vi. This is a longer walk, and therefore we have a contradiction. And now the proof is finished, because that means that this assumption was wrong. So W actually is an Euler Tour. So now we have shown the existence of an Euler Tour, and that was the other direction of the theorem. Okay. So let's now start with a new topic on directed graphs. And later on we will talk about Hamiltonian paths. And these are different from an Euler Tour in that in an Euler Tour every edge is used exactly once. In a Hamiltonian path we will have that every vertex is used exactly once. So we'll come to that a bit later. Okay, so what are directed graphs? Directed graphs are graphs where we have edges that have a specific direction. So we can walk from one point, from one vertex to the other. And, well, let me just depict an example. For example, we could have something that looks like this. We have V1, we have V2, V3. I may have an edge that goes like this, with an arrow. We use arrows in this case. I can go to V2 and V3. From V2 I may be able to go to V3, and from V3 to V2. So this would be a directed graph, as an example. We also call these Dijk graphs. And as you can see, we may have an edge that goes from V2 to V3, and also one that goes from V3 to V2. So these are two separate edges. So every edge has a direction. And we usually say that if we have an edge that points from V2 to, say, V3, then we call this the tail. And over here we have the head. So this is some notation that we may use. We also have now a different notion for the degree of a vertex, because we have different types of edges, essentially. Take, for example, V2. I have incoming edges and outgoing edges So that's why we are going to talk about an in degree and an out degree. So for example, the in degree of V2 is equal to, well, I have 2 incoming edges. And the out degree of V2 is actually something different. It's just 1 outgoing edge, so this is equal to 1. Okay, so this is some notation. So let's talk about walks. Let's figure out whether we can enumerate walks in a directed graph and compute those. So how many walks do I have, say, of length k that go exactly from, say, V1 to V3? How can I compute this? So I like to introduce adjacency matrices. You probably have seen them before, but let's go over this once more because the induction is also important. So let's do the theorem. So the theorem is this. Suppose we have a graph, then, and suppose it has n nodes. And we have the vertices V1 up to Vn. And now we let the matrix that contains the entries aij denote the adjacency matrix. For G. And what does that mean? It actually means that in this case, we say that aij is equal to 1 if we actually have an edge that goes from Vi to Vj. So this is an edge. And 0 if this is not the case. So this is the adjacency matrix. And now we can state something about the number of walks, directed walks, in a directed graph. So it turns out that this is easily computed by taking powers of the adjacency matrix. Okay, so let aij with superscript k be equal to the number of directed walks of length k that go from Vi to Vj. So we want to compute this, and it turns out that... Oh, wait a minute. So what did I do here? So actually let pkij be the number of directed walks of length k from Vi to Vj. Then what we can show is if you look at the matrix a to the power k, well, this actually is the matrix that contains all these numbers. So let me give a few examples. So let's take the matrix over here, look at its adjacency matrix, take a few powers and see what happens. So the matrix looks like this. If we just label the rows by, say, V1, V2, and V3, the columns by V1, V2, and V3, well, V1 has an edge to V1, V1 has an edge to V2, and also one to V3. V2 has only one edge to V3, so we have zeros here, and we have this. So this is the matrix A, and for example, if we compute A square, so how do we do this? How many of you know about matrix multiplication? And everybody knows? Well, anyway, so let's assume that you do know, actually. So that's pretty simple, right? So you take the column, you take the inner product with the first row, and so on, and you can easily compute this. And otherwise, you may want to do that yourself later on. And you get this particular matrix. And for example, a to the power 3 is something very similar. 1, 3, 3, 0, 0, 1, 0, 1, 0. Well, it turns out that if you look at this graph, and we, for example, want to know the number of walks of length 3 that go from V1 to, say, V2, well, let's see whether we can see those over here. Well, if I travel from V1 to V2 in 3 steps, I can go like this. I can go 1, 2, 3, so that's one option. I can go 1 and another 1 time, so it's the second step, and 3. I can also go directly over here and go back here and back over here. So it turns out that we can compute this. So how do we prove this? Well, we use induction, and the steps are pretty straightforward. So let's first define, because we want to prove that the kth power of A is equal to that matrix up there, where all the entries represent the number of walks. So let's say that Aijk, let this denote the ijth entry in A to the power k. And we want to show that this number is actually equal to the pijk for all the entries. So if you're going to use induction, well, it makes sense to assume that the theorem is, say, true for k. So the induction hypothesis could be something like this. The theorem is true for k. And this is really the same as stating that all these entries for all I and j, Aij is equal to the Pij k. So this is what we want to prove. And this is pretty straightforward, because now what we can do is we can start to look at how we compute walks of length k, or k plus 1. So let's first do the base case. That's how we always start. The base case is k equals 1. And we have essentially 2 options. So we want to prove this, so take an I and a j, whatever you want. So suppose we have an edge, vi, that goes to vj. Well, in that case, we know that the number of walks of length 1, well, is exactly, from I to j, is exactly 1, because there's this edge. So this is equal to 1. But this is also the definition of my adjacency matrix. So I can just write out here Aij 1. So that's great. So this case definitely works. Now, if there is no edge of this type, well, then we know that in one step we can never achieve Vj from Vi, because there's no edge. So we know this is equal to 0. There's no such walk. And this is, by definition of the adjacency matrix, also equal to the Aij. So this works. So the base case is easy. And the induction step is, well, it always starts by assuming pk. So that's, as you can see, these types of proofs always have the same structure. And in this case, we again assume pk. So now let's look at the, we want to prove pk plus 1. So what we want to know is, what's the number of walks of length k plus 1? So how can we express those? Pij k plus 1, how can we use this assumption over here? Do you have an idea? So we can have a, yeah.
Any walk of length k plus 1 can be gotten by taking one of, let's say from Vs to Vf.
Sure.
K plus 1 steps. You can go from somewhere from Vs to V in k steps, and then V to Vf in one step.
Yeah, that's true. So yeah, we could do that. So let's write it down. So what you're essentially saying is that you can enumerate all the walks by going of length k plus 1, by first going from I in, say, k steps to whatever v, and then in one step to, say, vi to v in k steps, and then in one step to v j. So let's write this down, because v can be anything. So what we do is we have a sum over all the v's, such that, well, we will use indices here. So let me do that a little bit differently. So let's say I have an h over here. So all the indices h, such that vh to vj is actually an edge in G. So then we can write out here that we go in k steps to vh. So how many walks are there? Well, we can use the induction hypothesis now, right? So we can say we go from I to h in k steps, and then, we can use this particular edge to complete it to a k plus 1th walk from I to j. So now, what is this equal to? Can we simplify this sum? We can, right? Because we know that there is an edge if and only if the adjacency matrix has a 1 in that particular position. So we could rewrite it and sum over all h from 1 to n. And then write pij k times, and then a j, oops, this should be an h. So we have the same over here. And then we have one edge from h to j. So I only count this number over here if this is equal to 1, and that happens exactly if there's an edge. I do not count this if there's a 0 over here, that is if there's no edge. But now we can use the induction hypothesis, because I know that these numbers are equal to the a's. So we rewrite this, and we see that we get aihk. So this is where we use the induction step, right? So it's like we assume pk over here. And I need to finish this formula. So we have this. Now by the definition of matrix multiplication, we actually see that this is equal to a k plus 1 ij. So the ijth entry in the k plus 1th power of the adjacency matrix. Here we have, this represents the matrix of the kth power. This represents the matrix of A. So we multiply essentially a to the power k times a, and we get a to the power k plus 1. And that's what we see here. So this is the induction step. And so this proves the theorem up here. Okay, so let's talk about a few more definitions concerning directed graphs. And then we will step into a very special type of graph, which are the tournament graphs up here. Okay. So one of the things that we have in undirected graphs, so where we have no directed edges, well, we talked last time a lot about cyclicity and stuff like that, and we talked about acyclic connected graphs. And we characterize those, or we define them as trees, and they have a very special structure. So what would happen here if we look at a graph, at a directed graph, and we wonder, what does it mean to be connected? Can we really talk about that? What does that mean? So, well, for example, if I look at this particular example graph over here, I can say, well, V1 has an edge that points towards V1 itself and towards V2 and towards V3. So maybe I would call this graph connected. But if I look at V2, I only see an edge that goes from V2 to V3 and not to V1. So maybe I do not call it connected. So that's why we define a stronger notion for a Dijk graph. So a Dijk graph GVE is called strongly connected. Oops. Strongly connected if we know that for every pair, so if for all vertices U and V in the vertex set, we actually have, there exists a directed path that starts in U and ends up in V in G. So this is what we would call strongly connected. And so now in undirected graphs, we had connectivity, and then we said, well, if a connected undirected graph has no cycles, we have trees, and they have special properties and all that. So what about this over here? Suppose we have an acyclic, strongly connected Dijk graph. What does that look like? So let's give an example, and yeah, it's not completely clear what kind of structure it has. So for example, I may have a graph that looks like this, for example. Say this is an acyclic graph, but I cannot really. It does not have at all a tree structure. So actually, the type of graph that we have here is called a directed acyclic graph. As you can see, there are no cycles because I only go forward, essentially. I can never go backward in this particular way that I depicted the graph. So a directed acyclic, so this is an example of a directed acyclic graph, but it does not look like a tree at all. So it's worth to define this separately, and we will use this on Thursday, when we'll talk about partial orderings. And it turns out that, as you can see here, a directed acyclic graph has really nice properties, and one of them is that you can order these vertices in such a way that you go from, say, left to right in a directed fashion. And that will lead to partial orderings as well. So that's something that we will talk about as well. Okay, so what's the definition? A directed graph is called a directed acyclic graph, and we abbreviate this by DAG. We call them DAGs. They're used everywhere, actually. If it does not contain any directed cycles. So these kinds of graphs are used in scheduling and optimization, and we will use them next week in the lecture on partial orderings. Okay, so now we have done a lot of definitions concerning directed graphs. So now let's talk about these very special ones, tournament graph, and see whether we can prove a few really nice properties, theorems about them. Let's see whether we can figure that out together. Okay, so what is a tournament graph? So in a tournament graph, I have a bunch of vertices, and essentially we want to represent like a tournament. So every vertex, say, represents a team, and a team can play against another team and beat them or lose against the other team. So we want to use the directed edges to indicate who is winning from whom. And such types of graphs have a very special property. So let me first depict one. So for example, we have E goes to A, goes to B, incoming edge from C, one coming from D, and over here we have this directed edge. We have this one. We have this one. Let me see whether I don't make any mistakes here. And this one. I think I've... oh no, and over here is another one. Okay, so what do we see in this graph? We see that either, say, team U beats team V, and that means that we have a directed edge from U pointing at V, or it's the other way around. V actually beats U, and we have a directed edge from V to U. So let's have a look at this graph and see how this works. So, well, for example, we have that B is beating E, and E is beating A, and so on. So let's have a look. Maybe we can figure out who's the best player in here. So this is sort of the general question that we would like to answer. Maybe we cannot answer this. So let's have an example. Does anybody see an example where, we have, for example, we start with A, and then we may beat another vertex, and maybe another vertex, and so on, until we have covered all the different vertices. Do you see a path that works like that? And that could give us an ordering on who is the best player. Like the one at the top, like A, is able to, for example, beat B. And B is, for example, able to beat D. And this one, E. And this one, C. So you would say, okay, that's great. Now I know that this one is the strongest player. But there's a little problem here, right? Because I can produce many such paths. And actually, if I look at C, then C beats A as well. So that's kind of weird. So wait a minute. We have that there's a directed edge from C to A. So it's like teams beat one another. And it's not very clear how we can talk about a best player. Well, we would have a best player if one player sort of wins from everybody else. So, but there's many examples here. So let's look at another walk. For example, C can go to B, to D, and then to E, and then to A. So there are many possibilities here. So this leads us to a concept. And we call that a directed Hamiltonian path. And we're going to show that in a tournament graph, you can always find such a directed Hamiltonian path. So what's a Hamiltonian path? This is actually an example of it. There is a walk that goes around the graph, and visits every vertex exactly once. So we're going to prove that a tournament graph has this beautiful property. Okay, so let's first write out a definition of this. A directed Hamiltonian path is a directed walk that visits every vertex exactly once. Okay, so as I said already, here we have such an example. Here we can go from A to B to D to E to C. Maybe there are even other examples. I did not actually see them. Maybe you can have a look at them as well. So maybe there's something that starts at B going to E maybe. That's a very different direction. Like this. That will be one as well. And so forth. Okay. So what's the theorem that we want to prove? The theorem is that we want to show that every tournament graph actually contains such a directed Hamiltonian path. Hamiltonian path. Okay. So let's have a look at how we can prove this. And so what kind of proof technique are we going to use? Maybe we can, do you have an idea? Like, well, usually we use induction, so that's what we're going to do here as well. But what kind of induction hypothesis can we do? So what would we induct on, you think? Maybe somewhere else? Maybe somewhere up there?
The number of nodes.
Yeah, the number of nodes. So we use induction on the number of nodes, and why would that be of interest? So let's have a look how we can think of that. So when you start thinking about such a problem, this is really sort of one parameter here. It's the number of nodes in a tournament graph. I also have edges, but if I think about edges, then I get it. If the edges is always directly related to the number of nodes in a tournament graph. So I really have just that one parameter. So it makes sense to use induction on the number of nodes. So we induct on n, where Pn is going to be that essentially the theorem holds true for a tournament graph on n nodes. So every tournament graph on n nodes actually contains a Hamiltonian path, a directed Hamiltonian path. Okay, so this is my induction hypothesis. So how can so when I think about that, I feel pretty confident, because if I look at the base case, that's how we always start. N equals 1. If n equals 1, I have just a single vertex. There's no edges, everything is fine, because the single edge is a directed Hamiltonian path. So this is great, so this works. So what about the inductive step? Now with the inductive step, we always proceed in the same way. We start to assume that Pn is true. Essentially the theorem holds for a two-dimensional graph on n vertices. Actually, let me keep this over here. So now let's think about how we can prove this induction step. So I need to prove Pn plus of n plus 1. And so how do I start? I have to start with a tournament graph on n plus 1 vertices. And somehow I got to be able to use this property, because that's what I assume. And that property only holds for a tournament graph on n points. So what would be a really good strategy to do here, to sort of proceed our proof? So let me first write out what we want to do here. And maybe you can think about how to advance here. So we have assumed Pn. Now we want to actually prove something about tournament graphs on n plus 1 nodes. So let's consider one. Consider a tournament graph on n plus 1 nodes. Now, how can I use my my induction hypothesis? So I start with this, and I want to use something that talks about a tournament graph on n nodes. So how could I proceed here? So, any suggestions? So what do you usually do, right? If I have like n plus 1 nodes, I have to somehow look, at least maybe there exists a subgraph in this bigger graph. So that's really how you always think about these types of proofs, also other problems. So there must be some kind of subgraph that already has this property. Well, let's take out one node and see what happens. Because then we have one node less, and maybe we will be able to apply our induction step. Okay, so let's take out one node V. And what can we say about the remaining graph? If we take out one node, for example, if I take out the node E over here, and I just look at all the rest, I can still see that for all the other nodes, either, say, U beats V or V beats U. So I still have an edge in one direction between each two nodes. So actually, I still have a tournament graph. So that's great. So this gives a tournament graph. So essentially, so far, we really haven't done anything creative or anything that we had to make a big leap in order to prove this theorem. We started out with, if you want to prove something like this, we have to really look at the number of vertices. And then we start to write down this stuff over here that makes total sense. And then we are going to figure out whether we can use this induction step. And so we just take out one node. And yes, it is a tournament graph on n nodes. So this is very systematic. That's what I try to get at here. So by the induction step, because by the induction hypothesis, I mean, we can use this, we know now that we actually have a Hamiltonian, directed Hamiltonian path. So let V1 to V2 to Vn be such a path. So now that we can use this, we apply it, and we get a path. So now, what do we want to do? We want to show that we can create a new path, which is also a directed Hamiltonian path, but now one that also includes V in the bigger graph. If we can do that, we're done. So now we have to start really looking at how we can make that happen. So, in order to do this, well, we have to see how we can somehow plug V, the vertex that we have removed, in this path over here. If we can do this we are in really good shape. Now, so far we haven't used at all, so that's also something that you can look at if you start solving such types of problems. We haven't looked at all, we haven't used at all the property that the tournament graph has, which I just wiped out. But so let's figure out what we can do here. So something, we should be able to use something. So of course, we have a few simple cases. For example, if V has a directed edge into V1, well, of course, then I have a longer, then I have a Hamiltonian path that goes from V to V1 to V2 all the way to Vn, and then I cover all the vertices exactly once, and I will have a directed Hamiltonian path. So this is great. So this is definitely easy. So this was case 1. And case 2, suppose that V1 has a directed edge to V. So now we have a little problem, because somehow there is an edge like this to V, but I cannot go like this. This is not a Hamiltonian path. I need to have a directed walk from that covers all the vertices exactly once. So now I have a little problem. So now we have to start really thinking about how we can solve this. So are there any suggestions to make this happen? So let's think a little bit about this. So somehow, right, if I start thinking about this, I would like to plug V somewhere in this sequence. That would be like a pretty obvious way to go ahead, yeah?
So in that case, V either beats V2 or is beaten by V2.
That is true.
And so whichever of V and V2 won comes first in the order.
Yeah, that's true. So for example, I may have that this one is, that for example V2 beats V as well, for example. But suppose that I have V3 over here and this one beats V3. Then, as you say, I could sort of plug V in here in this sequence and I may have a longer sequence. Or if this is not the case, then maybe the next one, V4, may have that property and I can plug V in here. So essentially what I want to show is that V is, I can plug V somewhere in the middle of two of these VI's. And the property that you were using is actually that you said, well, I know that V2 either beats V or V beats V2. So that's the property of the tournament graph that we're going to use here in order to prove this. So yes, that's a great observation. So now it would be, so the way you formulated it, we can maybe use induction, for example, to prove this. We can sort of try I mean, you sort of go recursively through this until you find the right spot. Maybe we can immediately precisely indicate such a spot. So how do we usually do that? If we are thinking about other theorems that we have tried to prove, yeah?
Where's the first place? What's the smallest value of I such that V beats VI?
Okay, so let's see. So what's the smallest value of I where V beats VI? Yeah. So what you're doing here is that you think about so usually we have words in our mind like largest or smallest or etc. And sort of an extreme position, and then we like to find out whether we can make that happen. And then we say, well, if that is not, if something goes wrong, we violate that smallest condition. Okay, so let's do that here. So let's indicate a specific spot. So you were suggesting, let's consider the smallest I such that V beats Vi. Okay, well, let's have a look how this would work. So this is a little bit of a different proof than what I had, but this should work fine as well. So let's see how it works. Okay, so we have V1, and we go to, well, first of all, we notice that, of course, if I equals 1, which that cannot be the case, so we know that I is larger than 1, so there's really somewhere a Vi minus 1. We have to check that, right? That exists, that this index is not equal to 0. It goes to Vi and then goes all the way up to Vk or Vn. So now we say we can use this, that V actually beats Vi. So now what about, so maybe someone else can help me here. I would like to have that Vi minus 1 beats V, right? That would be fantastic. Because then I have a path that goes from V1 all the way up here, goes there, and all the way up to here. So we have a directed Hamiltonian path that covers all the vertices exactly once, and that's what we want to prove. But why would there be an edge that goes this way? So so how do we reason about this? Maybe someone else in the audience up there?
Because Vi is the smallest number that V feeds, then anything smaller than I must have beat V.
Exactly. So, yeah, so if actually V would beat Vi minus 1, well, that would contradict this smallest property over here. So that's a contradiction. Now I use the property of the tournament graph. So now I know that Vi minus 1 must beat V. So I really have an edge over here. So that works. So this is the end of the proof. Now another version could have been in which we would do something similar like this. But we could also have used, say, the largest I, just something that you may want to look at. You can also use that the largest I, such that Vi beats V. We have a completely symmetrical argument here, but you could use this solution as well. So I'm just trying to sketch here the way of thinking that you may want to consider in these types of problems. So why would this work, by the way? Well, we have a similar kind of argument like this. We plug V right after Vi. We know there is an edge from V to Vi plus 1. Why? If it's not the case, there will be a larger index I. That contradicts our assumption that we have the largest I already. It's a tournament graph, so we know that there's an edge from V to Vi plus 1. And we get a directed Hamiltonian path as well. So you may want to look at that as well. Okay, so let's talk about so this is about the tournament graphs. So let's talk about an interesting tournament graph with a funny game. And this is actually a chicken tournament, like the chickens here represent the vertices, and they are pecking one another. But and there's a certain rule that defines a chicken to be the king chicken. So let's see how that works. Okay, so so that's a great application of graph theory. So so what do we have? We have that either a chicken U pecks a chicken V, and we say that U has a directed edge to V, so we're actually defining a tournament graph here. Or we have a chicken V that pecks a chicken U, and we get V has a directed edge to U. So we have a tournament graph, but now we define something new. we say that U virtually packs V if one of the two conditions hold, one of these two conditions. Either U, of course, packs V, so that's great. He's in good shape. Or there exists another chicken, W, such that U actually packs W, and W in turn packs V. So this is a very special kind of relationship. So we are wondering now, so U virtually packs V, yeah, so that's correct. So we are wondering now, can we now define something? Oh, is there a question?
Can there only be one chicken in between to be virtually pecked? There only like is one chicken in between you and the other one?
Well, there can be multiple chickens in between here, actually. So it's true that, you know, I may have several friends that help me out packing someone else.
Okay.
So when we were looking at these tournament graphs, we were wondering, you know, can we really indicate a winning player? Well, in this case, if we start to talk about virtual packing, when we look at the packing order, then, well, we can actually define something like a chicken king. So let me write that down. So, and actually, let me first explain what I mean here, and then give an example of a graph. Okay. So a chicken that is able to virtually pack everyone else, we will call a king. So chicken that virtual packs every other chicken, we will call, is called king, a king chicken. So let's give an example of a graph. So for example, suppose I have 4 chickens that know how to pack one another in this order. So who in the packing party here is going to be king? Do you see some solutions here? So take, for example, this one. So this one packs this one. Can it also virtually, because we talk about virtually packing, can it also pack this one over here? It does, right? It packs this one, and this one helps out, and can pack both this one and this one. Wow, that's cool. So this one is king. This one actually, well, let's have a look. It packs this one and this one. Can it virtually also pack this one? Yay. There's a friend over here that is doing that for him. So this one is actually also a king. So you can have multiple king chickens in here. What about this one? The same story. Packs this one, and yeah, and virtually, oh no, wait a minute, is this one? So, top one on the left. Oh yeah, over here. This. Yeah, so this one is king as well. Now what about this one? Well, it can pack this one, and then it's in one more step from here, because there's only one outgoing edge. It can virtually pack this one, but not this one. So this one is definitely the loser of the 4. So he's not the king. And so now what we want to prove is a theorem that sort of tries to identify one of the chickens that we know for sure is going to be king. So you can have multiple kings, but maybe there's one chicken that from our intuition we may feel is definitely going to be king. So what would be a good intuition? So we're talking here about virtual packing. We have this definition. So what kind of node in a tournament graph essentially would be, can we know for sure that is a king? Do you have an intuition for a theorem that we may want to prove? So that's often what we do in mathematics. We have some kind of funny new structure, and then we want to find out whether we can prove interesting properties about it. So we start to search for actual nice properties in theorems. So in this case, it makes sense that the vertex that has the most outgoing edges may be always king. So can we prove this? So that's what we're going to do. So that's the theorem. And let's see whether we can do this in an elegant way. So the theorem is that even though there are multiple kings as indicated in that particular example, that may happen, but I certainly know that the chicken that has the highest out degree is definitely a king. And the way we're going to prove this is by contradiction. Let's assume that's not the case. I mean, that must be really, really weird. I mean, if you are the one who has the largest out degree, it means that you can directly, just by yourself, pack the most others. So suppose you are not king. So by contradiction, so first of all, let U have the highest out degree. And we want to show that this U is king, so let's assume the contrary. So let's suppose that U is not king. Okay, so what does that mean? So let's look at the definition over there and see what it means that U is not king. So that means that both those conditions are violated, right? Because if one of those two holds, I know there must be one vertex V such that U does not virtually pack V. So I know that. So let's see what that implies. So I know that there must be a V such that U does not virtually pack V. So, well, maybe you can help me out. What does that mean? So it means that both these conditions are not true. So let's look at the first. So U packs V. If that's not true, and we're in a tournament graph, we know that V must pack U. So we have this. And we also know that the other condition, the second one over here, does not hold. So what's the negation of this second condition? Maybe you can help me out. So we have here there exists a W such that U packs W and W packs V. So how do we negate that logical expression? So for all, that's great. So for all W, what's over there is not true. So can we formulate that a little bit better? So it's not true that U packs W and W packs V. So that means that either, U packs W is not true, or W packs V is not true. So let's write that down. So we have that, well, let's just write it all out. So not U pex W or not W pex V. Well, how can we rewrite this? Well, it's a tournament graph, right? So we know that W pex U or this particular condition, which is V pex W. So maybe, so what do I have here? Is this going in the right direction? Well, I want to prove something about that. If I use contradiction, and I suppose that U is not the king, I've assumed that U has the highest out degree. So I want to show that I somehow violate that. So somehow I'm able to construct some vertex V, and by negating that U is not a king, it seems that this vertex V makes a really good candidate to show that it has a higher out degree than U. So let's see whether we can do this. We can rewrite this logical expression once more. We can also say that, well, if U pex W, so this is not true, then it must be true that this one holds. Because if that's not the case, then this condition is not true. So if U pex W, then this is not true. So then it must be the case that that is true. So V pex W. So now let's have a look at V. We notice that for all outgoing edges from U, there exists a similar outgoing edge for V. But V has one more outgoing edge. V actually is an outgoing edge to U. So what do we see here? That the out degree of V is actually at least the out degree of U, which is this particular condition over here that we show here. For all W, we have that this is true. Plus, and we have an extra one, is this one. Oh, but now we have a contradiction because we said that U has the highest out degree, but it turns out that we have constructed one that has a higher out degree. So that's a contradiction. That means that our original assumption is actually wrong. So suppose that U is not king was a wrong assumption, and U must be king. So that's the end of this proof. Okay, so this is the end of this lecture. So see you tomorrow at recitation, and next week we will continue with communication graphs and partial orderings.